Question is, when is the inverse of a function also a function? So we noticed that in one example we had a parabola, but when we switch the x and the y, then our parabola turns sideways, and that green one is not a function. And the green one's not a function because it doesn't pass the vertical line test. So the question is, how can we tell by looking at our original one, right? If I drew something, even a graph that we haven't done yet. This is a special kind of x cubed graph. If you flipped it, would it be a function or not? Okay. This one, when I flip it, looks like that. Is it a function? No. So how can we tell by just looking at the original graph whether or not the inverse is going to be a function? And it's something to do with the whole idea of the vertical line test and the idea with inverses that the x and the y switch. Now when I draw a vertical line, let's say I draw a vertical line on this one, how do we label an equation for a vertical line? Let's say the value is at 5. What would be on the left-hand side? Is it y equals or is it x equals? You're thinking vertical, you think y, it's actually x. Why is it x equals and not y equals for a vertical line? Well, if you labeled a bunch of points on here, right, you'd have 5, 5 maybe, you'd have 5, 4, 5, 2. What isn't changing? The x value is always equal to 5. So when we have a vertical line, we always label it as x equals 5. Now in an inverse, what's getting switched? The x's and the y's. So if I started just with a vertical line, x equals 5, if I did the inverse, it would become a horizontal line of y equals 5. So when my original parabola doesn't pass the vertical line, when my inverse doesn't pass the vertical line test, my original one doesn't pass a horizontal line test. And so when is the inverse of a function also a function? We can write the inverse is a function if the original graph passes a horizontal line test, then the inverse will pass the vertical line test. So the inverse will be a function only if the original function passes the horizontal line test. So when we go to example 3, it starts off with a parabola. Does a parabola pass the horizontal line test? No. If we did an inverse right now, we would get a graph that doesn't pass the vertical line test. This question says, figure out a way to restrict the original graph. And when you restrict the domain, you're only looking at some of the x values, not all of the x values. so that its inverse is a function. So first of all, if you only looked at half of the parabola, would it pass the vertical line test and the horizontal line test? Yes. So two ways to restrict this is to look at either the right half of the parabola or the left half of the parabola. So two ways, we could say, one, if I only looked at the right half, that would be when x is bigger than or equal to 1. That would be that half. Can you see that the blue one is just when the x values are bigger than 1? And if I wanted to look at when the x values are less than 1, that would be that half. Does that half pass the horizontal line test? Yes. It's only when we have both of them together that it doesn't. So if we restrict it by saying, I'm only taking half of the parabola, then my inverse is the function. Now when I take points, okay, first of all, I'm going to label the vertex, because it's a key point in black, because it's on both of them. I would have the point 1, 3. I'm going to label in blue a point on the blue half, which looks like we have these 2 points. We would have 2, 4 and 3, 7. And in green, I'm going to label some points 0, 4 and -1, 7. Write the equation of the inverse each time and use a graph to illustrate. So we're going to show this. We're going to sort of split our page up here in half. We're going to use the blue one first when we restricted it to x is bigger than or equal to 1. We're going to draw a graph of what results. If I draw a graph of what results, 1, 3, when I switch the x and the y, will become 3, 1. Again, I'll label that point in black because it was labeled in black on my original graph. What's going to happen to 2, 4? Oh, don't like where I labeled 3, 1. 2, 4 is going to go to 4, 2. 3, 7 is going to go to 7, 3. My graph, when it's reflected, is going to look like that. What is the equation of that graph? Two ways you could do this. One, you could say, I know algebraically how to find the equation of an inverse. Algebraically, to find the equation of an inverse, you switch the x and the y. So if I took my original equation here, y equals x minus 1 squared plus 3. If I switch the x and the y's and solved, well, I'd have to move my 3 over to the other side to get my squared by itself. I would have to square root both sides, not forget the plus or the minus. And finally, I would get y by itself as plus or minus x minus 3 plus 1. In other words, It's two different square root graphs. I'm wondering if you can see from this equation that the square root graph that we drew to begin with was the positive x minus 3 plus 1. You might even say, I could see that already, that it was a square root graph moved 3 to the right and 1 up. So I might have been able to get the equation just for my transformations as well. For the second one, when you only consider x less than or equal to 1, there's the restriction on our domain. When I go to graph it, I still have 3, 1, but now I'm going to have 4, 0, and 7, negative 1. This is a square root graph that's been flipped down, moved 3 to the right and 1 up. It's going to be, oops, I'm going to run out of room, I'll draw it underneath. The equation for this graph is going to be negative x minus 3 plus 1. So if we reread the question, determine 2 ways to restrict the domain. When you get this question on your quiz or your test, it's almost always a parabola that they use. And the 2 ways to restrict the domain is always based on the vertex. You either take this half or this half. So the way that I figured out x is bigger than or equal to 1, well, that's because my vertex, the x value, was at 1. So using that x value at 1, I can find out what's bigger than that and what's less than that. So my 2 ways to restrict the domain are based on my vertex and taking half the parabola each time. Write an equation of the inverse each time. So how do we find an inverse of equation? That's the work that we did in black. We switched x and y and solved for y, but with a parabola, when you square root both sides, you're always going to get plus or minus. One equation that's plus, one equation that's minus. Okay? A couple of things that you can do with that, because you have to figure out which one goes with which. In this case, the plus one went with x is bigger than or equal to 1. The minus one, the negative one, went with x is less than or equal to 1. How can you tell which one goes with which? Well, you could do a graph. And that's why color coding this right away, when I switched my x and the y values, my graph of the blue one was going up. And my graph of the green one was a square root going down. So I would say, oh, the square root going down, that has a vertical reflection. I would have needed the negative outside of my function to do that. So that can tell you that the green one needed to be negative, and the blue one didn't have a reflection. That one could stay positive. If my domain is restricted here to be x is bigger than 1, on my inverse, can you see that our blue graph, the y values are bigger than or equal to 1? Meaning that parabola would have to go up, meaning that it would have to be the positive one. Here, my restriction on my domain of my original one was x is less than or equal to 1. Notice on our graph, that our range is y is less than or equal to 1, meaning that square root keeps going down. Another way you could tell that that one has to be negative. All right, questions for practice on this are 10 and 12. For organization, it's nice to keep your two solutions separate, your two restricted domains, and you're restricting the domain of your original function separate and drawing the graph separate.